In this lesson, we'll be looking at complex zeros of polynomials. First, a little review. How many zeros does the following polynomial have? Remember, we can determine that by looking at the degree. The degree of this polynomial is 5. That means that we have 5 zeros. However, please be aware that that may not be 5 distinct zeros. You may not have 5 unique zeros. This could be due to multiplicity, or it could be due to imaginary zeros. So, fifth degree indicates 5 zeros, but again, that may not be 5 x-intercepts. Those could be due to multiplicity or imaginary zeros. Next, let's find the zeros of the following functions in both real and complex numbers. So to find zeros, remember we set the function equal to 0, and in this first one we'll simply subtract 9, take the square root of both sides, and we get plus or minus 3i. So we have 2 imaginary zeros. Notice that the degree is 2, and we do find 2 zeros. They just happen to be imaginary. In the next example, it looks like we have a third degree polynomial. It's been factored. So we're going to have 3 zeros. Again, they may not necessarily be distinct zeros. Let's see if we can find them. Set it equal to 0. And then we'll set each factor equal to 0. The first one we can see is simply 1. So we do have at least one x-intercept, or one real zero at 1. The next part, the quadratic, is an irreducible quadratic, meaning we cannot factor that. So we can't simply solve this using factoring. We'll have to use the quadratic formula. X is equal to -1 plus or minus the square root of 1 squared minus 4 times 1 times 1 all over 2 times 1. Simplifying, we get -1 plus or minus the square root of -3 all over 2. And if we simplify a little bit more, we get -1 plus or minus the square root of 3i all over 2. So it looks like we have 2 imaginary zeros and 1 real zero for a total of 3 zeros. So you'll have 1 x-intercept. The other 2 zeros are not x-intercepts, they're imaginary. To find complex zeros of a polynomial function, we follow the same steps as those in the previous section. So let's find the zeros of this function. We'll look at real and complex. Notice this is a 4th degree polynomial, so we should be looking for 4 zeros. Again, they may not be distinct. Some of them may be due to multiplicity or imaginary. To start, we'll start like we always do with potential zeros. To find the potential zeros, we look at factors of the constant, in this case 18. Factors of the constant 18 are 1, 2, -3, +3, then we get 6, 9, and 18. And then we divide by the factors, or the factors of the lead coefficient 3. So we get 1 and 3. Then we'll list out all of the possibilities. 1, 1/3, 2, 2/3, 3, 3/3, which is 1, 6, 6/3, which is 2, 9, 9/3 is 3, and 18. 18/3 is already there. 18/3 is 6. So these are the possible rational zeros. Once we have our calculator up, we will type in the function. Be careful not to make any typos. It's always a good idea to double check after you type those in. Make sure you don't have any simple mistakes there. And then we're going to either go to the graph or go to the table. It looks like, according to the graph, there might be one at -2, and it looks like the next one's between 1, 0, and 1. So we'll go to the table and find those. Confirm that -2 works. -2 is good. So in the calculator, we know that -2 works. And then we need to find the other one. Notice my x values are incrementing by values of 1. They're not incrementing by 1/3 like some of my values up here are. So to do that in the table, we can go to second table set, and we can change the delta table to increment, instead of by 1, we can increment by 1/3. And then go back to the table. And now let's look to see if that 1/3 is indeed a 0, which it looked like it was in the graph. 0.3 repeating is 0, and 0.3 repeating is a third. So it looks like our other value is 1/3. So we have 2 and 1/3. I'm just going to go back to my table and change that value back to 1. Most often, delta table set at 1 will give us everything we need. So I want to set that back before moving on. And once we have our zeros, we can start the process of division. Doesn't matter which one you start at. We'll just start at -2 since that's what I saw first. And we'll use synthetic division. So copy the coefficients of the original h, and we'll go through and do our division. Bring down the 3, multiply, add, multiply, add, multiply, add, multiply, add, and notice we get a 0. That's what we were hoping. We wanted to get a 0 remainder. So now notice that we have rewritten h. The factor that we just divided by is x plus 2. Remember, we divided by, it looks like a 2, or -2. This is the 0 generated by the factor x plus 2. So our resulting polynomial is what we have down here. These are our coefficients. 3x cubed minus x squared plus 27x minus 9. And since this is now a third degree polynomial, we want to do synthetic division one more time. So we'll use our other 0 from the calculator, 1/3, put it in the box. Just going to drop down those same numbers from earlier. Remember, bring down the 3 first, multiply, add, multiply, add, multiply, add. Notice we get a 0 remainder. That's a good indication that we're on the right track. We wanted that 0 remainder. So now if we're rewriting h, this time we divided by x minus 1/3. Again, the 0 is 1/3. The factor that we actually divided by is x minus 1/3. X plus 2 was there earlier, and then the result now is what we have down here. That is 3x squared plus 27. And so we have 2 real zeros. Those were from the calculator and from our division. Let's see, now we have a quadratic. We can solve this algebraically. So 3x squared plus 27, set it equal to 0, and solve. 3x squared equals -27. Divide by 3. X squared is equal to -9. Take the square root of both sides, and we get x is equal to plus or minus 3i. So notice we have 2 real zeros, and we have 2 imaginary zeros. -2 and 1/3 are actually x-intercepts. The plus or minus 3i are zeros, but they're not intercepts. Those are imaginary zeros. Next, we have the conjugate pairs theorem. Let f be a polynomial function whose coefficients are real numbers, and if z equals a plus I is a zero of f, then its conjugate is also a zero. And the conjugate we're going to denote as z bar. And remember the conjugate from back in chapter 1? The conjugate of z is a minus bi. You change the sign of the imaginary number. So this b becomes a minus b. For example, a fifth-degree polynomial has zeros 1, 5i, and 1 plus I. It's giving us 3 of the zeros. There's 5 of them, so we need to find the other 2. Since we know that 5i is a 0, its conjugate, negative 5i, must also be a 0. And if x equals 1 plus I is a 0, then our other 0 must be its conjugate, 1 minus I. So these are the 2 remaining zeros that when you add it to these 3, we get a 5 total. Fifth degree polynomial should have 5 zeros. Find a third degree polynomial with leading coefficient of 1 that has zeros 2 and negative 4 plus I. So we have a 0 of 2 and we have a 0 of negative 4 plus I. But it's a third degree polynomial. That means there's got to be a third 0. We can use our complex 0 to find the other. Negative 4 minus I must be the missing 0 because you have conjugate pairs. First, we'll write the answer, the polynomial, factored over the complex numbers. So that function f will look like x minus our first 0, which in this case is 1, times x minus our second 0, which they tell us is negative 4 plus I, and then x minus our third 0, which we just found to be negative 4 minus I. And to factor over the complex numbers, we want to take care of any of these double parentheses. So these second 2 sets we'll take care of. So f of x is x minus 1 times, here we'll distribute the negative sign. And then we'll do the same thing in the last part, distribute that negative sign. And now we have the answer factored over the complex numbers. Notice the factored version has complex numbers in it. Part B wants us to factor over the real numbers, meaning we don't want imaginary numbers in our answer. We don't want i's as part of our factors. So f this time, we'll copy the first factor. It's good to go. It's already real. To eliminate the imaginaries, we'll just distribute this out. So x times x is x squared. Then we get 4x. Then xi, 4x, 16, 4i, and then distributing the negative I, we get negative ix, negative 4i, and negative I squared. Now we need to go through and clean that up a little bit. Again, x minus 1 is already good. Let's combine like terms. X squared doesn't have any like terms, so we'll keep it like it is. Let's go through and find all the x's. 4x and 4x. That becomes 8x. And then we have xi, negative xi, that canceled. It should. We're trying to get rid of the i's. And then we have 4i minus 4i, they cancel. That's good. We're trying to get rid of the i's. And then we have negative I squared. Remember, by definition, I squared is negative 1, so that's negative negative 1 or plus 1. We have plus 1 and 16 gives us 17. And now we have factored over the real numbers. The i's are no longer part of our factor. Notice, to find the irreducible quadratic that generates imaginary or irrational zeros, we have this basic quadratic. Think ax squared plus bx plus c. Think of that basic quadratic when we're doing this. And we have a theorem. Every polynomial can be uniquely factored over the reals into the product of linear factors and irreducible quadratic factors. And that's what we basically did up here. Here we have a linear factor times an irreducible quadratic factor. Again, irreducible means that this cannot be factored across the reals. We can see that it factors across the imaginary numbers or complex numbers, but irreducible means we can't rewrite it as something pretty and linear like this. It has to stay an irreducible quadratic factor. So let's look at a special situation in this example. We want to find the complex zeros of this polynomial. Now, in the past, we looked for rational zeros using the test where we divide by factors of 36 and 1. But in this case, it's not going to work. These don't have any real zeros. And it's not obvious right away. This is going to come with practice. If you ever try to factor something and you don't get any real zeros popping out, then maybe there's a special situation such as this. Notice this almost looks quadratic. It looks similar to something that we've seen in the past. So we're going to use a trick that we've seen in the past. Use substitution. Let's let u be x squared. So that when we rewrite this, we get u squared plus 13u plus 36. And we're going to set that equal to 0. Again, we're trying to find the zeros. And now we can factor as if this were a regular quadratic. Two numbers that multiply to 36 and add to 13 are 9 and 4. Set each factor equal to 0. And we get that u is equal to -9 and u is equal to -4. Keep in mind we don't want u, we want x. So we're going to resubstitute. We know that u is x squared, so x squared equals 9, and x squared is equal to -4. Square root of both sides, we get x is plus or minus 3i. Square root of both sides, we get x is equal to plus or minus 2i. And this is why, if you tried it, we could not find real zeros because all four of them are imaginary. Again, fourth degree polynomial indicates 4 zeros. So let's factor this over the real numbers. If we want to factor this over the real numbers, we get f of x equals, we're going to go back to the use substitution here. We're just going to plug into this part what x is. X squared plus 9 times x squared plus 4. And now we've got the polynomial factored over the real numbers. If we want to factor over the complex numbers, we can use the zeros that we just found. F of x is equal to x minus the first zero, 3i. And then we have x minus the next zero, -3i. That's going to make this plus 3i. Then we have x minus the next zero, 2i. And then x minus the next zero, which is -2i, making this x plus 2i. And now we have the f polynomial factored over the complex numbers. Next, we want to use the given 0 to find the remaining zeros of f. So this time they tell us that 3i is one of the zeros. Keep in mind, complex zeros occur in pairs. That means if 3i is there, negative 3i must also be there. So we can use synthetic division using complex numbers. Same process, just a little more tedious because these numbers are complex. So 3i is a 0. We'll throw it into our box, list the coefficients of your original polynomial, bring down that first number, 1, and multiply. 3i times 1 is 3i. And then we add. We get 1 plus 3i. Then we're going to multiply. 3i times 1 plus 3i. 3i times 1 is 3i. 3i times 3i is 9i squared, which is negative 9. Add, and we get 1 plus 3i. Multiply 3i by 1 plus 3i, we'll get the same thing. Negative 9 plus 3i. Add, the 9's cancel, and we're left with 3i. Then 3i times 3i is 9i squared, or negative 9. Add, and we get a 0, which is what we wanted. We want a 0 remainder. Continue this process with the next 0. We know that negative 3i is a 0, so we'll plug negative 3i into the box. And I'm just going to bring down my values from earlier. Drop down that first number and multiply. Negative 3i times 1 is negative 3i. Add, we get 1. Multiply, we get negative 3i. Add, we get 1. Multiply, we get negative 3i. Add, and we get 0. Again, that's what we were expecting. We want a 0 remainder. So what we have now is a remaining quadratic, x squared plus x plus 1. So if we're factoring, we get f of x equals x minus the first 0 times x minus the next 0. It's going to make this plus 3i times, notice that we actually found this earlier, x squared plus x plus 1, we factored earlier at the beginning. So I'm going to come back up to the beginning and use that same info. Here's our zeros from x squared plus x plus 1. So let's bring those down. Negative 1 plus or minus the square root of 3i over 2. So this is going to get a little tedious. We need to write each of these separately inside the parentheses here. So we have minus the first value. Negative 1 plus the square root of 3i over 2. And then we have the next one, x minus negative 1 minus the square root of 3i over 2. And then if we go through and simplify this, f of x is equal to x minus 3i times x plus 3i. Now it gets a little tedious. We're going to go through and distribute this negative sign and distribute this negative sign. So the first time, we get x plus 1 minus the square root of 3i over 2. And then down here, distributing this negative sign, we get x plus 1 plus the square root of 3i all over 2. And now we have the polynomial factored over the complex numbers.